Martinez, and today I'm going to talk about a work titled Chimera, which stands for Clean Heterogeneous Image Datasets from Measurement and Label Noise for Rows Classification Accuracy. So, what is the problem that we have at hand? As we all know, insect pests are a problem in agriculture. In particular, they represent severe economic losses on food waste. How can we tackle this? We could apply more pesticides in the fields. However, we have to consider the presence of beneficial insects that we don't want to harm. And to avoid this, the idea would be to monitor the insect populations in the field so that we only act during critical situations. How can we do this? We can employ sticky plates. Sticky plates are placed around the fields, and once they are filled with insects, they are collected and analyzed. This can be done through AI models in computer vision, where we can detect the insects and detect their species. However, to be able to actually do this, we need lots and lots of data. Gathering this data is challenging due to the biological variability, the economic implications, as we need very specialized labelers, and also the fact that we are limited by the growing season. These limitations, we cannot do anything about it, is what it is, but there's a limitation that we can address, and it's the presence of noise. So when we have data sets, we might encounter situations where we have noise in it, and if we don't clean it correctly, this could hinder the training of the model, so creating confusion. What is the implication of this? That we will have lower accuracy compared to having a clean data set. An example of this can be seen here. We have a REST19 that is trained on both noisy datasets and its clean version. And as we see, there's an around 5% accuracy difference between one model and the other. So here we see that we need to tackle the noise because, yeah, it has an implication. But it's not only enough to tackle this noise, but to see the types of it. So there are different natures of noise. In particular, we saw two types of noise. The first one is label noise, which implies samples that are actually insects. So here, for example, we have a spider, but it's labeled as a fly, so it's incorrect. The other type of noise is measurement noise, which are samples that are basically corrupted or artifacts, like the one that is here. This is a border of sticky plates, but yeah, it could be dirt, for example. These samples, as you see, they are not usable as they are not insects at all. So they should be discarded. And that's where Chimera comes from. So as we said, we want to clean image datasets from measurement and label noise for actually getting a robust accuracy. The idea behind Chimera is as follows. So since we have these two types of noises, we want to handle them in diverse manners. So as I said before in the previous slides, measurement noise is unusable. It's not insects at all, so we should just clean it, remove it. But label noise instead, we should recover it because, as I commented in the sticky plate slides, there's a lot of limitations already. Like we have to wait for the summer, we have to pay a lot of people. So if we have this data already, it would be like more efficient to actually just relabel it. So what we want to do is indeed relabel this data and then give it put it again in the training pool to eventually train a classifier. So then how is it done? For the first step, we have the noisy dataset, and we train a model on this noisy dataset to get predicted labels. The idea is to group our samples based on these predicted labels. And why do we want to do this? Because of the following. So here we see two subsets based on the assigned labels, so the original ones. And once we give our samples to the noisy dataset, some of the samples may swap places. In this case, we have the predicted labels D1 and D2. What we see is that some of the samples swapped, and this indeed would be our potential label noise. Next step would be outlier detection. So after grouping the samples based on their predicted labels, we will give those groups based on the predicted labels to the outlier detector. Our pipeline is based on 80 events. 80 events starts by having this group of pictures, doing a feature extraction, in particular with a ResNet18, and then the feature vectors obtained go through an outlier detection. They have many methods available, as you see here, support vector machines, autoencoders, and so on. The selection of the method depends on what's best for the dataset. What we notice here is that no matter the outlier detection, the fact that the resonating output 512 dimensions was problematic. I'm going to show why. So in this slide, we see a 2D visualization in UMAP space of my 512 dimensions. In the left side, we see the true nature of the samples. So the blue is the measurement noise, the green is the normal samples, and the purple is the label noise. As you see, the measurement noise is quite separate from the other types of samples, so it should be easy to identify at least that one. Instead, what we see at the right side, we see that the green ones, which are the inliers, and the blue ones, which are the outliers, are at least nonsense from a human perspective. Like, we would expect the blue ones to be in the cluster and the left side, but that's not the case. Instead, if we reduced our 512 dimensions to 2D using UMAP, so the visualization that you see here, and then apply outlier detection, we'll get this, which now makes more sense. Like at least we see that, yeah, it's towards the blue area in the left side. Still, as you see, not all of the samples were detected, and this is not a surprise actually because of another limitation of Edge. And it's the fact that, yeah, even if we have many options for outlier detection, they require a predefined contamination rate. In particular, the default one is 10%. But even if we knew, like, we could tune it and give better results, in practice, we won't know beforehand how many outliers we have. So what we have to do instead is find a way to avoid this predefined contamination in the first place. So we propose an alternative method based on ACD scan clustering. So here we see a feature space in 3 dimensions. As you see, we have detected different clusters with ACD scan, and there's also some isolated points. The idea is to detect the largest cluster as the inliers in our space, whereas the other points either belonging to small clusters or to isolated points as outliers. To actually be able to make this work, we want to tune the hyperparameter space of ACD scan. In particular, we tune the minimum cluster size and the minimum samples, but not only, because also a way to make the clustering work is to do it in the right embedding space. So that also will affect the dimensionality of UMAP. So then we have to find the optimal hyperparameters for UMAP, so the dimensionality in this case, and also the ACD scan hyperparameters that I mentioned previously. How do we do that? We perform a grid search over different values of this, then created a clustering for each of these combinations, and then we score them. The scoring was based on the relative validity, which is a criterion that quantifies separation and sparseness of clusters, and yeah, gives a score. The higher, the better. So then the highest score is then selected, and we get our optimal hyperparameters that are then applied to detect our largest cluster, and therefore our outliers. So then our outlier detection is inspired by AD bench is modified in this way. So now we have a UMAP dimensionality, ACD scan step, and also the hyperparameter selection. So far we have talked about predicted label generation that served us for label noise, the outlier detection that was more focused into measurement noise, but now the last step is actually classifying the samples for cleaning. No? So for measurement noise, we have outliers. All the outliers are measurement noise. Instead, for inliers, if the predicted and the original labels are the same, are normal samples, and if they differ, are label noise. For normal samples, then we evaluate Chimera and train a model. We did this with the dataset that you see here. This is composed of 2 classes, the Tirolic minor fly and the carrot fly. And for each, we injected 20% of data for label noise and measurement noise in both the training and validation. The results that you see here, these are the detections. So you have 2 confusion matrices for the 2 classes. As we see, the measurement noise is almost perfect detection for the prediction. Instead, the normal and labeled noise are not perfect, but quite good, I would say. But as we commented, the end goal of this is to do classification. So how was the performance? Here, this is the first numbers that I gave you. So the 87 versus the 92% for noisy versus clean. and instead Chimera achieved a 90.5, so getting closer to the clean benchmark. Instead, if we had opted to just do 8 events, we wouldn't have improved anything. So here we see that, yeah, this is working. It's not perfect, obviously, but there's something to consider. And it's the fact that, yeah, AI is percent noise, quite noise robust. So even this 87.9% with 40% of noise, I would say is quite good. So yeah, the window of improvement was quite limited. Instead, there's also an interest in label noise, and this is important because, yeah, right now we just use the normal samples for training. If we had done it instead, we would have gotten 90.8% accuracy. So that's it. Thank you all for your attention. And if you have any questions. And the web code is in GitHub if you want to check it.
Thank you very much. There's time for questions.
Yes.
Thank you for a very good example. I can see this being very applicable in a wide range of areas, not just image processing.
Yep.
Anything where you have the risk of, well, particularly with mislabeling and so on, where you've got possibility of outliers, it's really important to be able to detect what is real data and what is noise from very different time. So I can see this being very applicable in a wide range of domains. Thank you very much indeed.
Thank you.
Other questions? Okay, well,
Thank
thank you
you.
very much. And then we have the last speaker in this session, Kumul Rujiselli. Sorry about pronunciation. Yeah, that's you, great.